proceed with other still simple examples. I consider axisymmetric turbulence. I yesterday defined what I mean with axisymmetric turbulence. I think here of inhomogeneous turbulence, where the preferred direction is defined by an intensity gradient. Or I think of a homogeneous turbulence under the influence of Coriolis force. Then the preferred direction, which defines the axis of axisymmetry, is the angular velocity omega, and I will also consider a originally homogeneous turbulence influenced by mean magnetic fields, and the preferred direction is defined by the mean magnetic field. We assume again that the mean electromotive force can be represented in this way with two terms only. Ignore higher spatial derivatives, time derivatives, and so on. Just in order to show the most important point. Yesterday, we said that Aij and Bijk are isotropic tensors, and isotropic tensors are in second rank are the Kronecker tensor, and of third rank the Levi-Civita epsilon tensor. Here, by the same conclusions, analogous to what we did yesterday, we must say that these tensors are axisymmetric tensors. That means tensors which don't change the component representation if you rotate the coordinate system. And you know, or you should know from mathematics, that second rank axisymmetric tensor can be represented in this way. It contains again the Kronecker tensor, contains the product of the epsilon tensor and the preferred direction, E, and contains EI, EG. And so also with B, here are already 8 coefficients. The B4 term acts on the Bj over dk and produces just the divergence of B, which is 0. So we can forget this term. And due to relations between the epsilon tensors and unit vectors like E, we may equate B5 and B6. So it makes...
Sorry about that.
Yeah?
These long equations, it's just from symmetry considerations.
It's just from symmetry considerations. It is a mathematical thing. Tensors which don't change the component representation if you rotate or change the coordinate system. Okay. This is a consequence for the electron. Oh, it will disappear. This is a consequence for the electromotive force. I have still 9 coefficients. I wrote it in a way that I have the curl of B here, made from the derivatives of B, and the symmetric part of the gradient tensor of B. Yesterday we simplified relations by introducing reflectional symmetry. Now, in the case of a gradient of the intensity, say the gradient points in the z direction, it is reasonable to consider reflections at a plane which contains the unit vector E. This is the direction of the intensity gradient. Then consider such planes, and it is reasonable to assume that you have reflectional symmetry with respect to this plane. It is again an exercise to take the expressions which I showed you before and to show that under these circumstances 5 of the coefficients have to be 0. And we have this relation. Or in the case of the Coriolis force, then you should not require reflection symmetry with respect to these planes. Otherwise, you would exclude that the Coriolis forces produces circulations. But you can require reflection symmetry with respect to planes perpendicular. This is preferred directions to the axis. And if you work this out, you see that all the coefficients which are connected with B itself, not with derivatives of B, vanish, and what remains is this. Okay, consider in more detail the case of inhomogeneous turbulence. We have then this. We can write Ohm's law in this way. We have two beta coefficients, and we can incorporate them in a now anisotropic mean field conductivity, which is given here. So -1 means inversion of the matrix. And yeah, when you consider then Ohm's law, or split it into components in the direction of the intensity gradient, parallel or perpendicular to it, you have this simple form of Ohm's law for the components parallel, and you have a bit more complicated form for the components perpendicular to it. We call the effect described by this term gamma effect. You see, it has just the structure of U cross B. That means gamma times the unit vector in the direction of the gradient acts like a mean velocity. And it transports mean magnetic flux or mean magnetic field, even in the absence of a mean motion. And it transports it outside of regions where the turbulence is intense, is high. So this is a region with high turbulence intensity. Here the intensity is lower. Then the flux is pushed out from this region. This region behaves like a diamagnetic material. And that was the idea, turbulent diamagnetism, elaborated in 1966. Another idea which belongs to this headline is the topological pumping. Consider convection pattern. I could take hexagons, I take simply squares. Here you have an upward motion, and around it you have a downward motion. In this pattern you can find magnetic field lines like this, which are completely in regions where the flow goes down. And so this flux will be transported to the bottom of the convection zone. You cannot find field lines which are completely in regions, in upflow regions. So if you consider, for example, this field line, then look from the side, you have this situation. It is deformed in this way. These are rather small structures which dissipate away, and the total effect is, again, that the flux is pushed to the bottom of the convection zone. That is the idea of topological pumping elaborated by Drobyshevsky and Yuforev in 1980. These are effects which are described by this gamma effect. By the way, you can treat the turbulent diamagnetism already in the second order correlation approximation, not the topological pumping, you must take into account higher correlations, because the correlation tensor, the second rank correlation tensor, which occurs in second order correlation approximation, is invariant under sign change of the velocity. But here it's important to distinguish between the upward and the downward motion, so you need higher correlations. And indeed, if you take them into account, you can treat this in this framework. Okay, I think I should skip this. Here are second order correlation approximation results for gamma. Essentially, the vector gamma E is a gradient of turbulence, a quantity related to turbulence intensity. Okay, consider the case of Coriolis forces. Then you have this other complex form of the mean electromotive force. You have again two beta coefficients, and you can, if you go to Ohm's law, you can put them into the mean field conductivity, which is again tensorial. It's a symmetric tensor. The next term is, you should read it, I gave it here, as coefficient omega cross J, the mean current. And then you can write Ohm's law in this way. You have here a term proportional to omega cross J. We speak of the omega cross J effect. By the way, this omega cross curl B can be rewritten in this way. There is a gradient which is without interest in the induction equation under the curl, and then what remains is a term which is derivative in the direction of omega of B bar. This is the essential. Okay, again, I think I shouldn't go into too much details here. You can calculate these coefficients, and I will return to this in when I speak about dynamo models, because this omega cross J effect is important for dynamo models. Okay, third example, turbulence under the influence of a mean magnetic field. If you take the formula which I delivered and you interpret E as the direction of B bar, then you can give a certain form of E, but since Lorentz forces, which are important, are independent of the sign of B, and in this consideration of the sign of B bar, we should require that E changes sign if B changes sign. And if you do this, you can write, or you can derive from the relations I gave before, such a relation for E, or here is a bit mathematics, there's an identity, and you can write at the end in this way. You see, this bracket is something like the alpha effect, but now first the alpha coefficient may depend on the mean magnetic field, and secondly you have a correction which goes with B curl B, B bar curl B, and then you have some kind of gamma effect where gamma is essentially the gradient of B squared, and you have again the beta effect. What is interesting in this example is, by the way, this is how to say, a starting point for considerations about quenching, for magnetic quenching.
Sorry.
Yeah.
But this,
Sorry?
it has been obtained just from symmetry considerations, right?
It is
So
just
that
from
is
symmetry.
not restricted to B bar being weak.
Not B bar is not weak, but what I assume here, is that the derivative of B bar is weak. So that
Why was this assumption? Okay, maybe
well, because I start from the representation E is AEJ B bar plus a term proportional to the derivative of B. And I have no other derivatives.
Okay.
And if I say that the coefficients depend only on B bar, I must assume that it is small.
So in this difference alpha minus alpha tilde, there is a small term so that you won't extend it to the case where it becomes negative, right?
Alpha tilde is not small, but it is connected with a quantity which I have to
So the factor in front of B bar, alpha minus alpha tilde and so on, won't become negative.
Sorry?
Would not become negative.
No, but alpha tilde can still depend on B bar. The
Uh,
modulus of B bar.
But still,
I cannot
if,
immediately-
if for large enough B bar and curl of B bar, this can change sign, right?
Yeah, but why?
Perfectly. It is a question of the further elaboration.
But isn't it true that alpha tilde can still be dependent on B bar?
Alpha tilde can depend on B bar.
And then you can always make sure it doesn't become negative.
Say at this level, I must say yes, it is possible. But you have, of course, to determine the coefficients in detail.
That's what
But
the
this
physics
can lead
says.
to
Yes.
very bizarre solutions.
Yeah, that's true.
I mean, he's not giving the solutions, he's just saying how they should look like.
I want to point out another aspect. No, again, a mistake. No. That is a place where I am. Okay. Next slide. I hope I make not again a mistake. So, one interesting aspect is you can write this result, which I derived, in using this relation. E is a term with B and a term with curl B. You can reproduce it by saying Rij is this effective alpha delta Ij and the gamma effect. But you can also say it is alpha, the original alpha, delta Ij, and you can put this term into the coefficient which describes the mean field conductivity. So it is no longer a unique relation. Okay. So far we considered homogeneous isotropic turbulence and now axisymmetric turbulence. But the turbulences we have, the kinds of turbulence we have to consider in mean field theory are in general more complicated. Say on a rotating body, the turbulence is influenced by the Coriolis force, and it has a radial gradient. Proportional to the gravity force, and perhaps even more. And then it is reasonable to write this E. That's right. No. Cannot see the. Yeah, it's very weak here.
Oh,
You can,
I have another one.
so, in between, I explain. It is reasonable. It is useful to consider this. You can split. Here. Thank you.
No, you're English. English thing. On the back side. Yes, this big part on the other side.
Yes, that's it.
Yeah. You can split the AJ into a symmetric part, which I called minus alpha ij, and antisymmetric part, which you can represent by epsilon ijk times the vector gamma. You can split the gradient tensor of B into a symmetric part and an antisymmetric part given by epsilon times a vector. And if you elaborate this, you see that this vector is essentially the curl of B. Then consider this term. You can write it in this form, second rank tensor times the curl of B, and a third rank tensor times the symmetric part of the gradient tensor of B. Now you can split again this Bij into a symmetric part and an antisymmetric part with a vector, say, delta. And if you do this, you find this representation of E. And you find Ohm's law in this form if you again introduce mean field conductivity which contains the beta tensor. And maybe you should look on the next slide. You have a term alpha times B. It is an anisotropic alpha effect. You have the gamma cos B term, now here, a general gamma. It is a gamma effect or pumping effect, as I explained to you. You have beta curl B. It leads to an anisotropic magnetic conductivity. You have the delta cross curl B. Let's call it delta cross J effect. Thank you. Delta cross J effect, in particular omega cross J effect, which I explained to you. But I'm here a bit more general. And you have a remaining part which I don't want to discuss so much with the symmetric part of the gradient tensor. In Ohm's law, you have again mean field conductivity, which is anisotropic. If you consider the U bar plus B bar term, you can put it together with the gamma effect, and you have here an effective velocity, effective mean velocity. And velocity which plays a role in electrodynamics, not in mechanics. Then you have simply U bar. But if you consider, say, transport of magnetic flux, you have this effective velocity. Not again anisotropic, and so on. Okay. No, skip this. How you can determine the structure of E in general, if you have influences of several vectors, say. Here I adopt the concept I explained to you in the first lecture of polar and axial vectors, or more general scalars and pseudo-scalars, polar and axial vectors, true or pseudo quantities in general, also tensors and so on. If you look at this relation, this is a polar vector. All the other quantities are pseudo quantities. B is a pseudo axial vector, and then so that you get a polar vector here, this must be a pseudo tensor, and this must be a pseudo tensor. Or in terms of this relation, you have a pseudo alpha tensor times B. You have the true vector gamma, and the pseudo character is made by gamma cross B. You have a true beta tensor times a curl B, which is again a polar vector. you have delta, think of omega for example, is a pseudo quantity, axial vector, and here again is a current, which is a polar vector, and so on. And you have to think which construction elements you have for your electromotive force under given circumstances. You have, in any case, the Kronecker tensor, a true tensor, and the Levi-Civita tensor, pseudo tensor. And you have, in the examples, we considered a gradient of, say, the turbulence intensity, which is a polar vector. You have the Coriolis, or the angular velocity defining the Coriolis force. It is a pseudo quantity, the axial vector. And in the following, we will consider, for example, U bar, and you can take the curl of U bar. I call this W. This is a pseudo quantity, the curl of a polar vector. And you can introduce, for example, the gradient tensor of U, symmetric part. Okay, these are possible construction elements. It depends on the problem you consider, which of these construction elements are relevant. Consider first inhomogeneous turbulence on a rigidly rotating body. So you have a gradient, you have the isotropic tensors, of course. You have a gradient of the turbulence intensity, or a related quantity, and you have, say, angular velocity, which defines the Coriolis forces. And then you must do some mathematics and make a list of the possible contributions to the alpha tensor. And here are these 6 possible contributions. I have it written so that the alpha 1, alpha 2, and so on are all scalars. G omega is a pseudo-scalar. Okay, and yeah, you rediscover here the alpha effect, now with G omega, which makes the pseudo property of this quantity. I have underlined this. It is one reason for an anisotropy of the alpha effect. On a rapidly rotating body, you have an anisotropic alpha which contains also this alpha tensor, which contains also this term, which is important for dynamo models. You rediscover here the gamma effect, but you have related quantities. Yeah, and so on. These are the beta and delta tensors. You rediscover here the vector responsible for the omega cos j effect. And yeah, this is only to show you that you have, for example, here, where a tensor which is symmetric in J and K, you have 18 coefficients, which you have, if you want, then to calculate, but you know already the structure. Okay. Next step. We include in the list of construction elements now also the curl of U bar and the deformation tensor, the symmetric part of the gradient tensor of U. And you have terribly long lists of contributions to this tensors. I restrict myself here on linearity in all these quantities, just to have a simple case. And you see in the alpha tensor, you have again the alpha effect due to G and omega. But you have also an alpha effect with G and W. That means the curl of the mean velocity. And you can have also an alpha effect with, let's say, deformation tensor, the gradient tensor of the symmetric part. Okay. It is only to show you what might happen. Beta tensor can have a contribution proportional to the symmetric part of the gradient tensor of the mean velocity. And here you can have omega, which leads to the omega plus j effect, but in the place of omega can also be the curl of u bar. And you have a similar effect. And so on. I think I should not explain this all in detail. Okay. Now what remains is you have to calculate the electromotive force, in particular all the coefficients, if you want all the coefficients I have shown you. And the question is what methods are available for this. I already explained to you the second order correlation approximation in the context of homogeneous isotropic turbulence. A bit more general, I have here included the mean velocity. You have to calculate u cross b, e, from with the help of this equation. You know, I explained it to you, in the second order correlation this term, which describes the fluctuations of u cross b, is cancelled. You can proceed to higher order approximations, so where in the equation for the nth order, you express the u cross b dash term by the results of the order n minus 1. And this procedure works, basically, and as Krause has shown a long time ago, it converges, but it is very tedious. So I know about a few calculations which were done by Stix and Niklas up to the fourth order, and I think that is already all. Nobody has really carried out this calculation up to arbitrary orders.
Could there be something wrong with the convergency proof? I mean, are we sure that it actually is correct? Or should it be
sometimes I had a doubt. I think we could speak about this doubt, but okay. Maybe I must add special conditions under the tree. So, then another method which exists only a few years is the test field method. I forgot to write the most important name here. It is Martin Schiller. And there are papers in the years 2005 to 2007. Papers where Matthias Reinhardt and myself and others are co-authors. And there this method was developed. Martin Schiller considered geodynamo models, simple geodynamo models, where numerical solutions are available, and he tried to extract from these simulations the mean field coefficients, the full alpha tensor, the gamma, the full beta tensor, and so on, all the 36 coefficients which exist there. And even more, he also included higher order derivatives. And then he constructed mean field models and tried to show, and he was successful, essentially successful to show that these models reflect the essential features of the numerical geodynamo models. So that the mean field concept works in this case. I have written down the basic idea here. You know that u cross b, or if you want to to calculate this, you have to solve the equation for small b here. And you remember also, hopefully remember, that I said E is a functional of these quantities, U bar, and B bar. And in this functional sense, it is linear on B bar. That means I can write down this relation where the Aij and Bijk depend on U and U bar, not on B, at least not in the functional sense. It can depend, they can depend on B via the U and U bar. Okay. Yeah. Now specify your B bar here to be a test feld. I call it a B bar N, and denote the corresponding B and E by Bn and En. Then this relation must apply. The coefficients Aej and Bijk don't depend on the test feld. They are independent of the test feld. So do it with many test felds. Write down such equations. The quantities designated by N depend on the test feld, or are the test field, not the Aij and Bijk. If you have a sufficiently large system of equations, n equal 1, 2, and so on, you can solve it for the Aij and Bijk. And this way you can calculate these quantities. Schöner did it in spherical coordinates, so it doesn't matter. This is the main idea of the test feld method. In between, it has been widely elaborated, in particular by the people around Axel, and applied to many other cases. The test fields should be linearly independent, so that the equations you get are linearly independent, otherwise you cannot solve them properly. The test fields should have no or only small higher order spatial derivatives, because we have assumed this in we have assumed this here. We have not taken into account higher derivatives, which we could, but let me consider first this level. The test fields need not to satisfy boundary conditions, and they need not to be solenoidal. You solve always this equation for B or then for Bn, and you know that the coefficients depend not on this test field. So there is no need to satisfy boundary conditions or take solenoidal fields. It is very, very convenient. The method works independent on whether U and U bar depend on B. So you can use it for investigations on magnetic quenching. Yeah, that I already said this. You can extend it to other ansatz for E, which contain higher order derivatives of B.
No, Franz, can I
Yeah?
raise a question here?
Yeah.
If you just go back, you said it's suitable for examining magnetic quenching. Yeah. This approach. Yeah.
Say it again. Is it?
You said it was suitable for investigating magnetic quenching.
Yeah.
But magnetic quenching is really concerned with the wave motion.
Yeah.
I mean, then you've got J cross B and influencing the U and so on. Well, I don't quite see whereabouts have you got the equation of motion.
You can write down the full systems of equations, including the equations of motion. And you have always to solve all these equations and calculate then the B and so on. You should not include the test fields in the equations of motion because quenching should take place due to the B bar, which is not the test field. Yeah. I have not written here all the equations of motion, but
yes, okay.
they belong to. And in the numerical schemes, Axel has, of course, all these equations are solved, and then you can calculate this. Okay, I give only one example. Again, I have forgotten to write down that it is a result of Sur, Axel, and Pandu. Here, for a homogeneous isotropic turbulence, the alpha effect normalized in a certain way, and eta t, it is beta, have been determined for a certain range of magnetic Reynolds numbers. This is a magnetic Reynolds number. Here you are in the region of low conductivity limit, and you have these quantities proportional to Rm. If you have only the analytical second order correlation approximations results, then you can speak only about small Rm here. This region. You see here that how these quantities behave for larger Rm. This is one result of the test field method. Okay. Now let us proceed now to kinematic mean field dynamo models. You can define, or you can write down the Maxwell equations, the average Maxwell equations. They have to apply everywhere, of course. Consider a simply connected conducting body in free space, surrounded by free space. Then in this body you have Ohm's law in this form, mean field version of Ohm's law. Outside you have, of course, no current, also no mean current. You should require that B vanishes at large distances from the body, at least like a dipole field, that means in this way. You can also write down the equations in this way. You can derive the mean field equation, the mean field induction equation in the fluid body. Here, you can say that curl B and divergence B are 0, or B is a gradient, there's a potential which satisfies the Laplace equation in outer space. You assume that there is no jump of the components of B across the boundary. It is quite clear for the normal components. It follows from divergence B equals 0. And it implies the assumption that no surface currents exist for the other two components. And again, this behavior of B. We speak of a mean field dynamo if these equations, or the equations given before, have solutions which don't decay in the course of time. That is our definition of mean field dynamo. Better, we say mean field dynamo model. At this point, of course, what exists physically, if it exists, is a dynamo. not a mean field dynamo. Mean field dynamo, you should say the mean field dynamo model. And if such a model works, then the dynamo works. But it is an abbreviation to say it is a mean field dynamo. Mean field dynamo is, strictly speaking, no physical entity. Okay, here are a few aspects of mean field dynamics. You can write down the energy balance now for the energy stored in the mean magnetic field, just as we did in the first lecture without thinking of mean fields. You have here a term, dissipation, which always acts against a dynamo, which leads to the decay of the magnetic field. You have here the action of the Lorentz force, and if you move the fluid against the Lorentz force, of course you enlarge the energy which is stored in the mean field, and you have here the corresponding term for the mean electromotive force E. Okay? Of course, mean field dynamo requires that the right-hand side is not negative. I already explained this. An interesting aspect is that mean fields are not subject to Cowling's theorem. The proof of Cowling's theorem uses the fact that in Ohm's law, this term has no component in the direction of B. It breaks down if you have a quantity here where you have a component in the direction of B. And so it breaks in general down on the mean field level. Except this term, which in the mean field case occurs here, has no component in the direction of B. It is an exceptional situation, and then Cowling's theorem must apply, of course. But in general, not. So you can have mean field models which are axisymmetric, two-dimensional, easy to take. Okay.
It is interesting that the same condition is what you require for helicity protection.
Yes, that's interesting.
Did I understand it now?
E dot B is what produces magnetic helicity.
Yeah, you're right. You're right. So it occurs in the helicity balance.
Okay.
Okay. I consider here a special kind of kinematic mean field dynamo models, which I call traditional models, with traditional assumptions. Consider a fluid body in which has a shape which is symmetric about the rotation axis, symmetric about the equatorial plane, and which is steady, and also the distribution of the magnetic diffusivity should have these properties. So it applies to all models of stars or galaxies also. Assume that all mean quantities which depend on the fluid velocity are invariant under rotation of u about the rotation axis, under reflection of u about the equatorial plane, and under time shift. It is again what you usually assume for stellar models or planetary models or models of galactic objects, at least in the first approximation. There are many consequences from this. One is you can split U in a U bar in a meridional circulation and in a rotation. And both these quantities are symmetric then about the rotation axis and the equatorial plane. So such quantities, like it is only to be considered as an example, U curl U, are under these assumptions symmetric about the rotation axis and antisymmetric with respect to the equatorial plane and steady. So alpha is, roughly speaking, equal to this quantity. And so alpha changes sign if you go from the northern to the southern hemisphere. It was reflected in the previous considerations by the fact that the effective alpha was G third omega, a coefficient which doesn't change sign if you go from north to south, and the sign change comes from this G is, say, radial, and the scalar product of radial vector times omega changes sign if you go to the southern hemisphere. And this is automatically implemented in these models. Okay, but there are more consequences. You can easily show that the solutions of the basic equations are superpositions of such modes. B depends, in the spherical case, on R and theta. This is the phi dependence, and this is a time dependence. Lambda and omega are real quantities. Where this B hat is symmetric about the rotation axis, and it could be symmetric or antisymmetric about the equatorial plane. Both types of solutions are possible, they are steady. We speak then of AM, antisymmetric modes, and we add M, which characterizes azimuthal dependence, or S modes. I have both on the next slide a few examples. An A0 mode, or the simplest example of an A0 mode, is a dipole field, an axisymmetric dipole. S0 is an axisymmetric quadrupole. The simplest example of this is an axisymmetric quadrupole. S1, here the fields are rotational symmetric about the axis. Here not. Here I have shown special planes. And S1 field is, for example, a field of a dipole which lies in the equatorial plane. So this is like this, but turned by 90 degrees, a dipole field. This is a bit more complicated. It is in the sense a turned quadrupole field. Okay. No? Too long? Yeah. AM and SM modes. We have, of course, a dynamo if lambda is non-negative. If you have omega equal to 0, this omega, you have a monotonic behavior of the fields in time. That means they grow or they decay. In the non-dynamo case, for omega unequal 0, you have an oscillatory behavior. If omega is unequal 0, and you consider the case m equals 0, you have an oscillation. It is, I wrote here, intrinsically oscillatory. You cannot change the system of reference, frame of reference, so that this oscillation doesn't occur. It is intrinsically oscillatory. If you think, for example, of solar dynamo models, you need these oscillations in order to reproduce the 11 years cycle. In the non-axisymmetric case, you have waves traveling in the azimuthal direction, and you can, of course, choose a frame of reference in which these waves disappear. You can go with these waves, and then you can transform this time variation away. Okay. As you have already seen, a few words, really a few words only about the basic dynamo mechanisms. I already mentioned somewhere that all dynamo models, or all dynamo mechanisms, consist of an interplay between the toroidal and the toroidal field. You can have dynamos due to the alpha effect, where the alpha effect produces a toroidal field from the toroid and vice versa. Okay, this is alpha, what we call the alpha square mechanism. It works with the alpha effect alone. You need no other induction effect. Most of the models, not all, deliver non-oscillatory fields. You have both axisymmetric and non-axisymmetric fields, and as soon as you have only the scalar alpha effect, you have a slight preference of the axisymmetric modes, A0 or S0, but if you take into account anisotropies of the alpha effect, you have in most cases non-axisymmetric fields, but the excitation condition for all these types of fields are very close together. The first model of this type was calculated by Steenbeck and Krause in 1969, and then I could add a long list of dynamo models which were investigated by other authors. Okay, this is the alpha square mechanism. Alpha omega. Then I should first explain this. Assume you have differential rotation. There is a body, conducting body, a non-conducting space outside, and this body rotates differentially. Say the surface is at rest, question of the frame of reference, and the inner parts rotate in the indicated way. If you have initially a colloidal field line here, then it is wound up in this way, and you can analyze this configuration so that the result is a superposition of the original colloidal field and toroidal fields here. So it means differential rotation produces, at least with axisymmetric fields, a toroidal field. So you can have a toroidal field from a toroidal one also with differential rotation. I write symbolically omega here for differential rotation. And if the differential rotation is sufficiently strong, then you can neglect the alpha effect for the production of the toroidal field, and what you get is an alpha omega dynamo mechanism. There are, depending on the special conditions, it can have oscillatory and also non-oscillatory magnetic modes, and it prefers, I will explain it, axisymmetric fields. Again, Steenbeck and Krause in 1969 the first model was used to model the solar dynamo. It was, if you think of this time, rather successful in explaining the solar magnetic fields. Yeah, preferably axisymmetric fields. The effect of differential rotation is very different on axisymmetric or non-axisymmetric magnetic fields. I explained to you this is an axisymmetric field. Here's the same. Then you can, with a sufficiently strong differential rotation, you can produce very strong toroidal field belts, arbitrarily strong in a sense. Situation is different with non-axisymmetric fields. Imagine you have the same situation here. You have originally a straight field line here. Then by the differential rotation, it is wind up in this way. Maybe you cannot see it in detail, but believe me, the arrows point in different directions. This, next to this, and so on. That means differently oriented field lines come close together. That means dissipation happens, and so you cannot produce a non-axisymmetric magnetic field in this way by strong differential rotations. That means the mechanism which explained to you here doesn't work, and that is the reason why no, other way around. That is the reason why an alpha omega mechanism preferably produces axisymmetric fields. The excitation conditions for axisymmetric fields are easier to satisfy than excitation conditions for non-axisymmetric fields. Okay. These both were dynamo models with alpha effect. But you can have also mean field dynamos without the alpha effect. So I cancel the alpha here. Then I need another mechanism to produce a poloidal field from the toroidal field. And the omega plus J effect is indeed able to produce a poloidal field from a toroidal field. And so you can have a dynamo completely without alpha effect with the omega plus Z effect combined with differential rotation. You observe non-oscillatory magnetic field, and again, by reasons which are connected with the differential rotation, preferably axisymmetric fields. Perhaps one remark. One remark. On the possibility or impossibility of a dynamo with omega plus J effects alone without differential rotation. Look at this energy balance. Assume there is no differential rotation. You have not this term. This is anyway a dissipative term. And if you insert for E here omega cross J, then already the integrand is equal to 0. And then also the integral. That means this effect alone cannot enlarge the energy which is stored in the mean magnetic field. You cannot have omega cross J squared dynamo. Okay, by the way, you can also construct other dynamos without alpha effect with with effects which are included in the beta tensor and so on, but I will not go into these details. There exist numerical models for this. Okay, so I'm at the end of this chapter, mean field electrodynamics, and let me say a few words about mean field, what I call, maybe not quite correct, mean field magnetic fluid dynamics. We are on the level without averaging. The basic equations are the induction equation, and we consider the momentum balance for simplicity in the incompressible case. Pressure term, inertial term, pressure term, friction term, Coriolis force, Lorentz force. If you subject now both equations to averaging, you have again the average induction equation, and you have the average momentum balance, and it's the same way in which here occurs mean electromotive force, E. Here occurs mean ponderomotive force, which drives motions, which is given by this. Yeah, I will not discuss the effects which are incorporated in F. I will only follow up the branch which is defined by E. But in the presence of the equation of motion. Okay, it is analogous to what I already explained. You have now an equation for little b or small b and for small u, and b and u are now functionals of b averaged and u averaged, and if you have an external driving force of F. So also E and F have this structure, and they are not necessarily linear in B bar and U bar. Okay. We relax now the assumption we made for all the other considerations that B decays to zero in the case of vanishing mean magnetic field. That means we admit now a MHD turbulence. And to see what are the consequences, let's split U in a zero part with no magnetic field, and a part which vanishes if the magnetic field goes to zero, and B is the same. Then you have, again, E equal to E0 and plus E B. The E0 results from U0 plus B0, and the EB has three terms. You see it here, or you can take this term and this term together here, and then it remains this term. Okay, what we have discussed so far is just this term. All our considerations which we made so far are a discussion of this term. We have not discussed this E0, and we have not discussed this other contribution with B0 to the EB. And I will give at least two examples for these terms. Consider, again, homogeneous isotropic, but now magnetohydrodynamic turbulence. Consider B as small and ignore an influence of the mean flow. Then we have, by symmetry reasons, again E equal alpha times B minus beta curl B. We have no E0 term because in the isotropic case it must be an isotropic vector, and we have no isotropic vector. By definition, there is no isotropic vector. If you adopt the equations I have given before, oh, sorry, it's the wrong direction. If you accept these two equations with omega equals 0 and okay, and expand then U and B in this way, a term independent of the magnetic field and a term which is linear in the magnetic field, and of course higher terms. And if you introduce in both equations for U1 and B1 the condition for a second order correlation approximation, you know it already in the case of the equation for B, and make a similar assumption in the equation for U. It is in fact the neglect of the nonlinear term in the equation of motion, in the equation for U1. Then a calculation which I don't want to show you in detail leads to this. You can calculate the alpha, which occurs here, and the beta, which occurs here. And the alpha is, yeah, I think it should be look familiar to you, with the exception that I have the zeros here. These are indeed the velocity fields for in the limit b equal b tending to 0. And you have another term here, which you have not seen so far with the p zeros. And you have a beta term which is only one term. Perhaps you can better see what this means if you go to the high conductivity limit and the low viscosity limit, defined in this way. Then alpha u is just minus 1/3 u curl u. This is zeros here, and a characteristic time. And there is another term, alpha b, with b curl b. This is 0. The 0 is important. If you wouldn't have it, then this would disappear. Get an additional term which we have not included in the considerations before. Interestingly, in the case of beta, you have only a term with specific. Okay. This is an
Good
example.
Comments?
Yeah.
I mean, we have for a long time discussed that the 0 can be dropped, and with Sharanya.
Wait a moment.
Yes.
The answer is no. It cannot be dropped. Yeah. Yeah, I will give an example for this E0. Consider an originally homogeneous isotropic MHD turbulence, but influenced, that's why I say originally, now by a mean motion, u bar, and by a Coriolis force. Then you can show it, and the first who did it was Yoshizawa in 1990, that you get an electromotive force independent of the mean magnetic field, completely independent of the mean magnetic field, with this structure, a coefficient times curl of u bar, the how it is called, the vorticity of the mean vorticity, and coefficient times omega. It turns out that these coefficients have something to do with the cross-helicity, u times b. If you make again a second-order correlation approximation, you find these results. G eta is the Green's function I have given in the lectures before. G nu is just the same with eta, the magnetic viscosity replaced by nu, the kinematic viscosity, and here is the quantity which of the type of the cross-helicity, and the omega, you have this relation. You have, under these circumstances, and if you have cross-helicity unequal 0, you have, let's say, battery terms in your equations. You have electromotive forces which can drive currents independent of the existence of a mean magnetic field. So this is the simplest example for this E theorem. So, last remark, and then I come to your question. You can, if the equation of motion available, small u is available, you can derive an equation for the time derivative of the electromotive force. Of course, you can calculate it in this way. You know this from given by the equation of motion, and you know this given by the induction equation for small u. Assume here that you have no mean motion and no Coriolis force. Then you can elaborate this, and you get for ET for the time derivative of the electromotive force 3 different terms. The first I give more or less explicitly. You can show that this looks like the sum coefficients, one I gave here, times ij times bj, and another coefficient which looks a bit more complicated, that's why I didn't write it down here, times derivative of b. The other terms are the dissipative terms, with mu and with eta, and a term which results from the forcing. I write F triple because I use the equation of motion after eliminating the pressure, and then I have to modify the force a little bit. The last term, in this term I put all the third order terms in UB. So U cross U, and you have to multiply it by B. This is the third order term. Or the Lorentz force B cross curl B, and you have to multiply it by U. This is the third order term. Okay, so far so good. You have such an equation which you can use for whatever you want. Sometimes, often, people make this ansatz. This is rather, it's clear, you have clear expressions for this. It is not so clear what this means and what this means. And there are, I should say there are people who say, I put the sum of y and z equal to minus e over a characteristic type. It seems plausible in the absence of the magnetic field, then this term x is absent, then E should decay to 0. And if you replace the remaining Y plus Z in this way, you have just an equation which describes the decay of the electromotive force. Whether it describes the decay really correctly is an open question. If you use this ansatz for E, you can immediately conclude that your electromotive force has this structure. No higher order terms, according to the derivation I showed you. Just this structure with the Aij and Bijk given by the A triple Aj given on the slide before, and the B triple times tau not given on the slide before, replaced by 3 dots. So this is an interesting relation. In the isotropic case, you can reduce it immediately to this relation. A contribution given by the velocity field and a contribution given by the little b, and for both the same time constant t asterisk. For beta you get only one term. This relation is very often used and very often quoted. The problem is that I don't know a clear justification for this answer. It looks plausible, but I don't know a clear justification, and I think nobody knows it. Or at least nobody explained it to me. Here there are some assumptions which are not clearly formulated and which then put restrictions to the region of validity of this equation. There must be some restrictions of the velocity. If you look back on second order correlation approximation, in this case, this B is proportional to B bar, then this term is proportional to B bar squared, and you can imagine that it's small compared with this. But in the second order correlation approximation, you find here an expression which is not so simple, which contains the history of u, correlation between u at the time t and the time t minus tau, and this integrated over tau, and also the neighborhood, the spatial neighborhood of u. You have expressions with here x plus psi, and here x, and here x plus psi, and that's integrated over psi. So there is some deviation from the in a certain frame, well-established second order correlation approximations, second order correlation results. It looks very reasonable, but it doesn't totally coincide with other results. I would be glad to give an explanation why it deviates. I cannot give it to you. And with this open question, I think I should. Oh yeah.
Okay.
I should finish here.
Thank you, Carl.
Thank you very much.
Questions, please.
About test field level, I wonder, how do you choose the right test fields?
Sorry?
How do you choose the right test fields for that?
How I took test fields. You are free to choose test fields. They have only to satisfy the condition that they are independent from each other, so that you have system of equations for the A and B, which you can solve, where the solutions are uniquely defined. Otherwise, you are completely free. I explained you need not to take solenoidal fields. You need not to take fields which satisfy the boundary conditions. Was this your question? No.
But regarding the form of the fields, I think we have different opinions on that. Because we know that the higher order terms in the derivatives eventually cannot be dropped anymore.
Okay.
And of course, in that case, with the test field method, we can still calculate the correct result by going to infinite order, or in other words, doing the kernel calculation in spectral space. And that means we have to calculate in Fourier space or in spectral space, for example, all the high wave number contributions. So it does actually matter then what is the form of the test field.
Okay, I don't disagree.
Yes, please.
Can you maybe please explain again how this omega cross J effect works, how to convert toroidal and poloidal fields without alpha effect? What you want to call the black hole?
Remember that I said that omega was can be split into two terms. One is the gradient, and the other one is, I think, at the minus omega E1. That's uninteresting gradient term. Assume this is in the z direction, then you have here the z derivative. Now consider the dynamo model where you have a phi component, the phi, and you have to apply it on b phi. And at the moment when b phi varies with that, then you have an effect, you have, also b phi over bz at the same place at which you have otherwise the alpha effect. There's no alpha effect, but at the moment when there is a variation of b phi with z, then you get a term at the place where usually the alpha term is. Usually you have alpha b phi. By the way, alpha changes sign from north to south, so that you have here the other sign. If you assume that b phi is antisymmetric with the equatorial plane, this so in the dynamo models you have also here different signs. So it works like another.
So is it as important as the alpha if the alpha is also there?
Sorry?
If the alpha effect is also there, then is this term as important?
Then is the question what dominates.
Yes.
And I think in all or most natural objects, the alpha effect will dominate.
Why?
The alpha effect has something to do. You have alpha E, and the alpha is connected with the gradient of the turbulence intensity.
Yes.
So I can write, I can estimate this by something divided by a scale A. Here I have the z derivative. Say you have a large scale variation of E phi here. I characterize the large scale
But if
by
you have a thin disk,
capital L. And so I think that this effect is in general smaller than this effect.
but if you have a thin disk,
Yeah?
then both should be compatible.
You can think of special situations where the
Accretion disk or the galactic disk, where maybe both are important.
A few years ago, I tried to stimulate Anwar that he should make galactic dynamo models with the omega Pasteur effect. I think it happened not so far.
I remember this, but I heard that, sorry.
Maybe.
So you should amplify
Yeah,
advances.
we discussed it quite in detail, but
Yeah.
Yes.
Now, I would be glad to find examples where the omega Pasteur effect dominates. So far, this is the theoretical possibility.
It's called the radler effect, so therefore,
Yes, that's why I would be glad to find examples where it really works. Not only
it's
where it
important.
exists,
I mean,
but
it works, of course. We know it, but
yeah,
it's important.
you can in artificial models. Yeah, and by the way, also in the geodynamo models investigated by Schreiner, he found non-zero contributions to this delta coefficient of the omega Pasteur effect, but not strong enough so that we could say, yeah, the Earth is the omega Pasteur dynamo.
There's a close cousin, possibly, which is called the.
Sorry?
There's a close cousin to this effect, which is the shear current effect.
Yeah. I implicitly I mentioned this when saying you have, in addition to the omega cos D effect, you have a W. W is the mean vorticity. Yeah. And this is what is sometimes discussed in terms of the shear current effect.
Okay. If the sign is correct, I mean, then it works.
Or if it's non-zero.
Good.
It's okay.
Good. So with this, let's then have our break. And thanks for hands again. And then we will continue with your talk, I think, afterwards.
I can try with my laptop today.